It's a pleasure to have, I will welcome back everyone to the Symplectic Zoominar. It's a pleasure to start off with Igor Uljarević, who will talk about contact non-squeezing by selective symplectic homology.
Thank you very much for the invitation. Obviously, contact geometry is at least as rigid as smooth topology, for it has an additional structure, namely the contact distribution. How far contact geometry goes beyond topology is currently an active topic of research. In this talk, I will try to answer the question whether contact geometry actually remembers not only the shape, but also the size of an object. There is no natural metric in contact geometry, and there is no natural volume form. Therefore, the usual tricks to define, to measure the size do not work in the setting of contact geometry. In the absence of volume form, natural one, and metric, a convenient way to address the notion of size in contact geometry is via contact non-squeezing. We say that a subset of a contact manifold can be contactly squeezed into another subset B if there exists a contact isotopy that takes A inside B. If it happens that the contact manifold M, the ambient, is open, then we additionally assume that the isotopy is compactly supported. The most basic examples do not promise much as far as size and contact geometry are concerned. So there does not exist any non-trivial, non-squeezing on the standard R2n-1. This is because on R2n-1, there exists a homotopy-like family of contact homomorphisms that can squeeze any bounded set into any neighborhood of 0. Of course, this family is not compactly supported, but we can consider its contact Hamiltonian and cut off as far to the end as we need. So we can make any given contact isotopy, including this one, compactly supported, and preserve anything we like in a compact subset. Since the standard contact sphere without a point is contact homomorphic to R2n-1, this implies that there is also no non-trivial contact non-squeezing on the standard sphere. And moreover, since any contact manifold locally looks like an open subset of R2n-1, this means that there is no non-trivial contact non-squeezing on any open and on any contact manifold locally. In other words, on a small scale, contact geometry does not remember the size. Quite surprisingly, there are some cases where there exists non-trivial contact non-squeezing on a large scale. This was first observed by Uljarević, Kim, and Polterovich. They considered the pre-quantization of Cn, so the contact manifold Cn times S1, and they considered the product of the ball of radius R that sits in Cn times S1. So this set, the ball of radius R times S1, can be contactly squeezed into its interior if and only if the radius is strictly smaller than 1. So obviously, the ball of radius R times S1 can smoothly be squeezed into itself for any R. So this is really purely contact geometry claim. Uljarević, Kim, and Polterovich, they proved the case where R is either less than 1 or an integer. Chiu completed the theorem and proved that what happens when R is not necessarily an integer. And there are alternative proofs by Fraza and Sander. So the punchline here is that there exists sometimes a non-trivial contact non-squeezing on a large scale. A consequence of my work is non-squeezing on Ustilovsky spheres. Ustilovsky spheres are contact manifolds that I'm going to define after I state the theorem. So in every Ustilovsky sphere, there exists two smoothly embedded closed balls of maximal dimension, such that one of them cannot be contactly squeezed into another. Those balls are really balls. They are not balls times S1. And of course, in smooth category, embedding of any closed ball can be made arbitrarily small by a smooth isotopy. So now let me tell you what an Ustilovsky sphere is. An Ustilovsky sphere is a special example of a Briscoe manifold, where the first exponent is a number that is equal plus or minus 1 modulo 8, and all the other exponents are equal to 2. Ustilovsky used these Briscoe manifolds to construct exotic contact structures on standard smooth spheres. So they are all diffeomorphic to the standard smooth sphere. And moreover, sometimes it even happens that the contact distribution on an Ustilovsky sphere is actually homotopic through smooth distribution of hyperplanes to the standard contact structure on the sphere. So we see here that an Ustilovsky sphere exhibits non-trivial non-squeezing, and that the standard sphere, to which Ustilovsky sphere is diffeomorphic, does not. And we also see that the reason why this theorem holds does not lie in contact distribution up to homotopy through smooth distributions. Actually, the theorem on Ustilovsky spheres is a special case of a more general theorem that concerns Liouville domains with infinite dimensional symplectic homology and whose boundary is a homotopy sphere. So if W is a Liouville domain of dimension at least 4, such that its symplectic homology is infinite dimensional, and such that its boundary is a homotopy sphere, then the same conclusion holds. There exist two embedded closed balls, smoothly embedded closed balls, such that one of them cannot be contactly squeezed into another. Smooth non-squeezing is trivial on homotopy spheres. This is because every homotopy sphere actually admits a Morse function with precisely two critical points. And one can use the gradient flow of such a Morse function to squeeze every non-dense subset into any non-empty open subset. Actually, by the same method, we can prove that there exists contact non-squeezing on the boundary of every Liouville domain that has infinite dimensional symplectic homology. But sometimes it happens that this non-squeezing is actually also topological non-squeezing. So the role that is played here by homotopy spheres is to make sure that we get something that is topological squeezing, but contact non-squeezing. By removing a point from a sphere, one gets a Euclidean space R to the K. So the previous theorem can be used to actually prove that there exists an exotic contact structure on R4m plus 1 that exhibits non-trivial contact non-squeezing. And this contact structure is actually a tight contact structure. So it is an exotic tight contact structure, and contact non-squeezing is an indirect way to prove that there exists an exotic tight contact structure on R4n+1. So the standard contact R4n+1 is not contactomorphic to any Ustilovsky sphere with a point removed. Along these lines, I'd like to mention a result by Floer, Chaplot, and Helfer. They prove that there exists infinitely many pairways not non-contactomorphic tight contact structure on R2n+1 if n is bigger than 1. So the corollary is a special case of their theorem. In order to prove non-squeezing results that I just mentioned, I constructed a version of symplectic homology that I still call selective symplectic homology. It relies on classical symplectic homology, especially the version by Viterbo. And it resembles the relative symplectic homology by Varolganas. And in a way, it can be thought of as an open analog of relative symplectic homology. So selective symplectic homology is homology that is associated with a Liouville domain and an open subset of its boundary. In this figure, it is colored red. And also, when I say Liouville domain, I consider Liouville form as part of the data. Intuitively, selective symplectic homology is obtained as a direct limit of the Floer homology groups for Hamiltonians on the completion of W, whose slope tends to infinity over omega, but remains close to 0 and positive on the rest of the boundary. In this slide and the next one, I'd like to compare selective symplectic homology with the symplectic cohomology of a Liouville sector.
Just a second, maybe you said it and I missed it. Do you make any particular assumptions on omega besides it being part of the boundary? Does it need to have
Actually, on omega, there are no other assumptions. So it can be only it can be any open subset of the boundary, including empty set and including the vaulting.
Thank you.
So there are no assumptions. And so Ganatra, Pardon, and Schende introduced the notion of Liouville sector. In simple words, oversimplifying, it's just a Liouville manifold with boundary. And among other things, they also constructed symplectic cohomology for a Liouville sector. Is denoted as symplectic cohomology of X relative its boundary. The notion of a Liouville sector is closely related to the notion of stops on Liouville manifolds. This notion was introduced by Silvan. So let me define a stop on a Liouville manifold. To define a stop, first I have to pick a codimension 2 Liouville manifold, meaning Liouville manifold that has a dimension by 2 less than dimension of Liouville manifold X. So I'll call that codimension 2 Liouville manifold F. So a stop is just a proper codimension 0 embedding from the product of F with complex half plane, so embedding into X, that respects in certain way the Liouville form. Namely, the pullback of the Liouville form on X has to be equal to the sum of Liouville form on F plus the Liouville form on the complex half plane plus some correction term that is just the exterior derivative or just differential of compactly supported function. So as I said, the notions of a Liouville sector and a stop on a Liouville manifold are essentially are related, and in fact they are essentially the same. By removing a stop from a Liouville manifold, one obtains an example of a Liouville sector, and other way around, every Liouville sector can be obtained by removing a stop from a Liouville manifold. Now, a Liouville sector has a cylindrical end, just like Liouville manifolds, and it should not be confused with its boundary. And symplectic cohomology of a Liouville sector is basically, we take Floer cohomology of a Liouville of a Hamiltonian whose slope tends to infinity over that conical end. So you can see that selective symplectic homology has the same flavor as the symplectic cohomology for a Liouville sector. So with at Liouville sectors, in the context of Liouville sectors, for symplectic cohomology, one physically removes part of a Liouville domain, Liouville manifold, and then takes the direct limit when slope tends to infinity. And in selective symplectic cohomology, one specifies which part of the boundary should be ignored. And then we let the slopes tend to infinity on the remaining of the boundary, meaning this omega. So let me now restrict our intention to the case where both selective symplectic homology theory and Liouville sector theory work well. So I will take for a Liouville manifold to be the completion of the Liouville domain, and I'll take sigma, a stop on that Liouville domain. I'll take Liouville sector to be the complement of the image of the stop, and I'll take omega to be part of the boundary that is not covered by the stop. So here is the completion of a Liouville domain, and here is a stop on that Liouville domain. Now on the right, you can see which part of the Liouville manifold is relevant for symplectic cohomology of the sector X. And on the left, you can see which part of the Liouville domain is relevant for selective symplectic cohomology. So the key part is this is a part of W, so the compact part of the completion that intersects the image of the stop. So it is an interesting question under what conditions actually those two groups, those two theories actually coincide. Now there is a difference between selective symplectic homology and symplectic cohomology for Liouville sectors that is more on the technical side. So Liouville, so symplectic cohomology for Liouville sectors to bound, to prove compactness, it uses arguments by Groman. Whereas the selective symplectic homology uses Alexandrov maximum principle. So actually it uses it indirectly because it uses Floer homology for contact Hamiltonians that I'm going to talk about on the next slide. And this Floer homology for contact Hamiltonians uses a version of Alexandrov maximum principle. And finally, the difference that so that is related to the question Sarah asked shortly ago. Selective symplectic homology is defined for any open subset of the boundary, and not necessarily the one obtained by removing a stop. So now let me recall the Floer homology for contact Hamiltonians. This Floer homology was introduced by Will Mary and myself some time ago. And the setting is the following. So again, I take a Liouville domain W. I will call its boundary sigma. Then we take a contact Hamiltonian on that boundary, possibly time dependent, but it has to satisfy two conditions. First, its time one map is not allowed to have any fixed points, meaning the contact Hamiltonian has no one periodic orbits. So this is equivalent, not equivalent, this is analog of requiring that slopes, constant slopes, are not periods of Reb orbits in the classical symplectic homology theory. And the second condition is not really a strict condition. It's just that HT is one periodic in time variable. So now, given such Hamiltonian H, contact Hamiltonian HT, we choose a Hamiltonian on the completion that is not degenerate and that has slope HT, lowercase ht. There are many such Hamiltonians. So we pick one, and there is always at least one of them because we can cut off R times H and obtain one. Now, what Mary and I proved is that the Floer homology for such Hamiltonian H is well defined. And we also proved that there exists a continuation map from Floer homologies, from Floer homology for H to Floer homology of F, if H is less than F or equal to it outside of a compact subset. In particular, if H and F have the same slope, then we can define continuation maps in both directions and prove that actually the continuation map is isomorphism. So if H and F have the same slopes, their Floer homologies are canonically isomorphic. This allows us to talk about Floer homology for contact Hamiltonians. And also, the continuation maps descend on the level of Floer homology for contact Hamiltonians. So Floer homology for contact Hamiltonian, from continuation map from Floer homology for contact Hamiltonian H to Floer homology for contact Hamiltonian F is well defined if the contact Hamiltonian H is less than or equal to the contact Hamiltonian F. Now, ideally, we'd like to define symplectic homology by taking the direct limit of Floer homologies when the limit goes through the set of all contact Hamiltonians that are supported in omega. So something like this. So we take, this line represents the boundary of W. The red segment represents the open subset omega. And this is a graph of some contact Hamiltonian H. So ideally, we'd like just to take the direct limit when H becomes bigger and bigger. However, this is problematic because unless omega is the wall boundary, the contact Hamiltonian H has a plenty of one periodic orbits. Namely, every point in the complement of omega is a constant orbit of H. So this H is not admissible. For that reason, we take an additional step in the construction of selective symplectic homology. We perturb the contact Hamiltonian H by a positive perturbation. Then we let the perturbation tend to zero along the way, taking inverse limit of Floer homology groups. And only after that, we take the direct limit with respect to H. Now, on the next slide, I'm going to repeat this definition, but just more rigorously. So I'll denote by H omega the set of contact Hamiltonians H that are non-negative, such that they are strictly positive on omega, and they are zero elsewhere, such that the one periodic orbits of H are constant. So in particular, this implies that no one periodic orbit of H intersects omega. And finally, I assume the derivatives of H up to order 2 vanish on the complement of omega. Very often, this third condition is implied by the other conditions. For instance, if the complement of omega is equal to the closure of its interior, then the third condition is not necessary. However, if, for instance, the complement has an isolated point, then this is not true. We need this third condition so that the inverse limit that we use in the construction of selective symplectic homology stabilizes. So for sufficiently small perturbation, Floer homologies will be isomorphic. Now, by pi of H, I denote the set of perturbations. That's just the set of smooth functions on the boundary that are positive everywhere, and such that H plus F has no one periodic orbits. Note that H plus F cannot have a constant one periodic orbits, because F is positive and H is non-negative, so H plus F is strictly positive. And now the symplectic homology is the direct limit when H goes through H omega of the inverse limit when F goes over the set of perturbations, or the Floer homology for the sum of H and F. If the set omega, the open set omega, is equal to the wall boundary, then selective symplectic homology recovers classical symplectic homology. And the other extreme is when omega is equal to the empty set. In that case, selective symplectic homology recovers the singular homology of W relative its boundary. So, or said differently, in this case, selective symplectic homology is isomorphic to the Floer homology for Hamiltonian that has small and positive slope. It is possible to define other versions of selective symplectic homology, such as positive selective symplectic homology, S1 equivariant symplectic homology, selective symplectic homology, and positive S1 equivariant selective symplectic homology. However, in this talk, I won't use these versions.
But the idea in the equivariant version is that the action should somehow preserve omega? Or
actually, it's that we will just take autonomous Hamiltonians. So the slope is autonomous. We take autonomous Hamiltonian, and then this S1 action is not a geometric action on the boundary, but it's the action of translating the one periodic orbits. So we do not require that omega is S1, is invariant under some S1 action. But it is sometimes useful when it happens that the symplectic homology is zero for some Liouville domains, let's say for the ball. And then when that happens, by taking S1 equivariant positive symplectic homology, one obtains a lot of generators nevertheless.
cool. And again, the action here is on the Hamiltonian, not
Yes.
on the boundary.
The action is actually by shifting the time interval. So
I see. Thank you.
So now I will recall some properties of selective symplectic homology that are relevant to the proof of non-squeezing results. First, selective symplectic homology actually depends only on the ideal Liouville domain and the subset of its ideal boundary in the sense of Giroux. So this is not reflected in the notation, but it nevertheless holds. So what I mean by this, I will explain in the following figure. So we take a Liouville domain, W. These lines represent the flow lines of the Liouville vector field. We take an open subset omega on the boundary. And now let us choose a different Liouville domain that has the same completion. So that means we take we choose a boundary this time that intersects all the flow lines that start at the boundary of initial Liouville domain. I colored by red the projection of the set omega to the new boundary with respect to Liouville flow. So the Liouville flow projects omega to some new subset. And then I consider a new Liouville domain. So selective symplectic homology for the situation on the left is canonically isomorphic to the selective symplectic homology for the situation on the right. So this is what I mean that selective symplectic homology is actually an invariant of ideal Liouville domain and an open subset of its ideal boundary. Selective symplectic homology behaves well with respect to direct limits. So continuation maps for Floer homology for contact Hamiltonians give rise to continuation map for selective symplectic homology. It's defined whenever omega A is subset of omega B. And now if we take a sequence, increasing sequence of open subsets of the boundary, then we can take their direct limit with respect to these continuation maps. And what holds is that this direct limit is canonically isomorphic to the selective symplectic homology of the union. Union here is denoted by omega. So the canonical isomorphism is furnished by continuation maps. So conjugation isomorphisms is a family of isomorphisms for selective symplectic homology that are used to prove that actually contact isotopic subsets that they have isomorphic selective symplectic homologies. So conjugation isomorphism is associated with a symplectomorphism of the completion that preserves lambda outside of a compact set. Every such symplectomorphism gives rise to a contactomorphism of the boundary that we call the ideal restriction. This contactomorphism is actually the first coordinate of the symplectomorphism psi. Of course, if we happen to be far into the conical end. Now, the conjugation isomorphism that is related to psi maps selective symplectic homology for omega to that of the pre-image of omega under the ideal restriction. So I didn't actually write down exactly how this conjugation isomorphism is defined. So it basically maps generator gamma, a closed orbit, to the psi inverse composed with that closed orbit. So it should be a contravariant factor. The conjugation isomorphisms commute with continuation maps. Now, whenever we have a contactomorphism that is contact isotopic to the identity, that contactomorphism is the ideal restriction of some symplectomorphism. This is because we can choose a contact isotopy that takes that contact homomorphism to the identity, consider its contact Hamiltonian, and then multiply that contact Hamiltonian with the radial coordinate r and cut off. And so we obtain, and then we take time-one map of that symplectic Hamiltonian. This is shortly how one can prove this. Since the conjugation isomorphisms commute with the continuation maps, this means that in particular, this number r of omega, which is defined as the rank of the continuation maps from selective symplectic homology of omega to classical symplectic homology, it means that this number, r of omega, is invariant under contact isotopes. I will call this number shortly rank of omega. So the non-squeezing results that are consequence of my work are actually consequence of the following theorem. If r of omega A is less than r of omega B, then omega B cannot be contactly squeezed into omega A. Apart from r of omega being invariant under contact isotopies, this theorem uses also the factoriality of the continuation maps, meaning the composition of continuation maps is a continuation map itself. So in order to get some interesting consequences, some interesting examples of non-squeezing, it is enough to find families of subsets that have small selective symplectic homology and the ones that have big rank. So on the next slide, I will show how one can prove that sufficiently small Darboux chart has small selective symplectic homology. So I will actually take a subset of a Darboux chart that's a contact polydisk. So here is a definition of contact polydisk. It's analogous to polydisk. It's just that we have one coordinate, z coordinate, that is a bit unusual because its dimension is actually 2. Oh, 1, sorry. Then we bound the norms of these coordinates. Okay, and here is the proposition. If W is a Liouville domain, any Liouville domain, and if P is a contact polydisk in a contact Darboux chart, then the continuation map from the selective symplectic homology for the empty set to selective symplectic homology for the interior of the polydisk is an isomorphism. And if you remember, the selective symplectic homology for the empty set is isomorphic to the singular homology of W relative its boundary. So the guy on the left has dimension less than the sum of Betti numbers of W. We'll consider that small. So the proof of this proposition is by analyzing the dynamics of the contact Hamiltonian of the following form. Here, R has n coordinates. Each coordinate, and theta also has n coordinates. Rj and theta j are polar coordinates in x, j, yj plane. And so one can prove that actually for such a contact Hamiltonian, that z coordinate is strictly monotone along the trajectories of the contact Hamiltonian. So proving that there are no closed orbits. And in fact, one can pass from epsilon to h continuously without creating one periodic orbits. And this is essentially an essential ingredient in the proof of the proposition above. So even in the simplest cases, the computation of selective symplectic homology is somewhat challenging. So it was possible to find way through this problem for Darboux chart by analyzing contact dynamics in a Darboux chart. But however, if you want to prove that there exist non-trivial sets, subsets with big selective symplectic homology, we stumble upon more serious obstacles. So before actually giving examples of sets that have big selective symplectic homology, I will introduce a notion of immaterial subsets. An immaterial subset of a contact manifold M is a subset such that there exists a contractible loop of contact homomorphisms on M that is positive over A. So by this, I mean the following. So there exists a loop of contact homomorphisms that is contractible on M, such that its contact Hamiltonian at the time t and at the point x is positive whenever x is in A and for all times t in R. So a set consisting of only one point is always immaterial if the contact manifold has dimension at least 3. However, in dimension 1, this is not true. So point is not immaterial in S1. Now let us now take a Liouville domain whose selective symplectic homology, that has infinite dimensional symplectic homology and whose dimension is at least 4. Now let us take a circle, embedded circle, that is immaterial and transfers to the contact distribution. If the dimension of W is at least 4, we can always find such a circle in any Darboux chart. So there are plenty of such circles. And let us now take omega to be the complement of gamma. Now in the situation just described, the rank of omega is infinite. So in particular, the rank of the complement of a point is also infinite. Using the nice behavior of selective symplectic homology with respect to direct limits, this theorem actually implies that there exists a sufficiently small Darboux chart such that the rank of its complement has arbitrarily large rank. So this is going to be an example of subset where the rank is big. And again, this is not true if the dimension of W is equal to 2. Now let me finish the proof of non-squeezing. So let us take so I will prove that there exists so let me recall first the statement. So we have a Liouville domain W whose symplectic homology is infinite dimensional and such that its boundary is a homotopy sphere. And then on such a sphere, we have two embedded closed balls of maximal dimension such that one of them cannot be contactly squeezed into another. And here in the figure, you see the boundary of a Liouville domain W. You don't see the W itself, just its boundary. Now, since this boundary is homotopy sphere, homotopy sphere, then there exists a Morse function with precisely two critical points. I'll call them N and S. I will denote by omega S the polydisk in a Darboux chart. And as we saw, the rank of this polydisk, omega S, is finite. It's actually bounded by the sum of Betti numbers of W. Then I'll take a sufficiently small Darboux chart centered at N, and I will choose this Darboux chart so small that the rank of the complement is bigger than the rank of omega S. I can do that because of the theorem on the previous slide, which says that I can make rank of the complement as big as I wish. Then if I choose the value of the Morse function to be sufficiently close to its minimum, then its sublevel set will be contained in omega S. And therefore, this sublevel set will have rank less than or equal to the rank of omega S. As the value approaches the maximum of F, eventually this complement will contain the sublevel set will eventually contain the complement of omega N. And in this case, the rank of the sublevel set will be bigger than the rank of the complement of omega N. So this means that the Morse function F has two values for which the sublevel sets cannot be contactly squeezed into one another. For which the sublevel set with respect to one value cannot be contactly squeezed into the other sublevel set. And as we know from the Morse theory, all these sublevel sets, when C is between minimum and maximum of F, are actually topologically balls. And so this is the proof of the theory. I will stop here. Thank you very much for your attention.
Thank you. Question.
I have a question. So by the proof you showed, it's not completely clear to me why to demand that the symplectic homology is infinite dimensional and not just like dimension is bigger than the dimension of relative homology of W in the boundary.
Yes, so I think that actually you are right. I think I can relax that condition.
Oh,
so,
okay.
Yes, so I think so.
I have a lot more other questions, but maybe other people should go first.
So I just wanted to be on the safe side, so to give myself a lot of space.
Very safe, very safe.
Yes.
Can I ask you a question? Why did you use gamma to be immaterial? And then I have the impression that you only use that the point is immaterial. Just before the slide before that, I think.
Oh,
Previous
yes.
slides. No, not this one.
Yes.
Probably 21.
Yes.
Yes. So here you start by saying that a loop is immaterial, and then I have the impression you're only using that a point is immaterial. Am I wrong?
You are not wrong, but I think the thing is that to prove, so I actually proved that the complement of immaterial circle has infinite dimensional symplectic homology in this setting. The same proof goes through if I take immaterial subset, but that is such that there exists strict contact Hamiltonian. Sorry. So the same proof goes through if I have a subset that is foliated by Reb orbits. So because in this case, I can play with strict contact Hamiltonians, the ones that are fixed along Reb orbit. So far, I haven't proved that if I take any subset that is immaterial, that its complement is infinite dimensional. So the point cannot be foliated by the Reb orbits, and that's why I first did with circle. First proved the statement for the circles, and then concluded afterwards that the same holds for the point. So, having said that, I believe that actually the complement of immaterial subset has infinite dimensional selective symplectic homology. But I haven't done it. I haven't tried, to be honest. I haven't tried hard enough because I could prove all the applications without it. It's simply the computation is more complicated because I'm playing with the composition of contact flows, and then if the contact Hamiltonian is not strict, then some conformal factor pops up and complicates the story.
Okay, so in your case, gamma will be a Reb orbit, and then you.
Yes, with respect to some contact form.
So
I can. Yes,
okay.
But if gamma is transversed to the contact distribution, I can always find the contact form such that this particular gamma is its Reb orbit.
Okay, thank you very much. Thank you.
More questions? I mean, I have an annoying one, maybe sort of going back to the question of the divisible omegas. In the definition of the selective homology, when you take this H plus F and you put conditions on H, I mean, the comment you made was about maybe sometimes the third condition of the derivatives up to second order vanishing is on the complement is kind of automatic and sometimes not. And I was wondering if maybe you could, if there is hope to formulate a condition that would be equivalent and purely topological.
Well, you mean to formulate the condition such that I can omit the third?
So basically, instead of imposing an analytical condition on the H, imposing a topological condition on omega.
That can be done, but it's not complete. Meaning that I will, if I do this, I restrict the family of subset omega. So meaning, so I can, for instance, take that the complement is equal to the closure of its interior, and then it holds. But it's maybe a bit stupid because it's not very smart. It's the first idea.
Yeah, so it would not be like you could have conditions that would imply it, but it's not going to be an equivalent condition. It will be a stronger one.
Yes. So this condition that I said, it implies it.
Right,
but it restricts the number of subsets.
I see.
Because I'd like to work also with the complements of a point, let's say. And now if you take omega to be complement of a point, then the third condition is not really implied by the other two. And yes, it's actually, I don't know, maybe without this third condition, maybe one can still have the theory. I don't know, it's simply that it is very difficult to work with such a theory, because then the inverse limit is difficult to compute. Because if I have the third condition, I know that I get this inverse limit. So by inverse limit, I mean this guy here. You see the arrow, right, of the mouse. So yes, by the third condition, I mean this, by the inverse limit, I mean this limit. So the third condition implies that if that I can always take sufficiently small f, such that this inverse limit is actually the same as hf, h plus f. So I can kind of omit the inverse limit, and that simplifies the situation significantly.
I see. Thank you.
But maybe one can prove some technical analytical lemma that will say you can do everything even without third condition. Everything is nice. But I have doubts about it.
More questions?
Yes. Say you take Morse function on the boundary and you look at the sublevel sets, and for each sublevel set you look at this rank that you defined. So can you relate this as you change T to something related to the Morse function?
Actually, I don't know. I think that it is very difficult to do because, for instance, with these homotopy spheres, they are just spheres. So we can choose. So they are diffeomorphic to spheres. No, they are homomorphic to spheres, right? So, and then basically Morse theory is very, very humble in this case. So there are two critical points and nothing happens in between. So yes, we can consider this rank and increase the level set continuously, and at some point something will happen, right? And then one can ask, is there some geometric object lying there where something happens? But that object is definitely not a critical point of F. It's something more subtle. But maybe
yes, I understand.
Maybe there are more subtle things in Morse theory that can be related to this. But appears to me that one cannot really ignore just the contact distribution. So maybe one can define something using Morse function and its behavior regarding contact distribution, and then obtain something. But I don't know. So I think I'm still thinking about these things, and I think one can cook up something. One can extract something like that from this story.
Uh-huh. Mm-hmm. Okay, thank you.
Okay, maybe let us thank Igor again.
Thank you very much.